Welcome back to the next lecture. Today we will look at some different aspect, but that small difference makes a very large difference in the processing of the equations and so on and so forth. Okay. The aspect that we are going to look at today is, of course, we are still at mass flux. However, so far we looked at steady state diffusion. Today we are going to look at unsteady state diffusion. Recall what steady state is. The properties of interest at a particular point in the system do not vary with time. That is steady state. If it varies with time, then it is unsteady state. Okay. Because the properties don't vary with time, we could put the time derivatives to 0 earlier. We cannot do that here. To understand this, it's worthwhile repeating the concentration of the diffusing molecule at a particular location changes with time. If it's pure diffusion or diffusion in a membrane and so on and so forth, this is what is actually happening. To understand this a little better, let's again look at it from the framework of a problem, the context of a problem, and that problem is something like this. Surface modifying agents, SMAs for short, are used to promote or dissuade cellular growth on the surface of interest. Sometimes it's used to promote and other times it's used to dissuade. It's used to dissuade, for example, growth on the hull of a ship or a container handling cell solutions. You don't want cell growth there. Therefore, you could use a surface modifying agent to modify the surface of the hull of the ship or the container handling cell solutions. The surface is sometimes exposed to the SMA containing solution for a certain period to effect the modification. You just contact the surface to a liquid that contains SMA, and there will be transfer of the SMA onto the surface, and that is what treats the surface with the SMA, with which attributes desirable properties to the surface. Let us take the case of a thin surface sorbing SMA from a solution with SMA concentration C0. Okay, the solution has an SMA concentration of C0 and the thin surface is sorbing that. The thin surface is placed at the bottom of the vessel containing the SMA solution. There is no movement in the solution after the placement of the surface. Let us consider the case when the amount of SMA sorbed is a very small fraction of the total SMA amount present in solution. In such cases, the SMA concentration far from the surface does not appreciably change. I have asked you to think about it. Why don't you think about it? If you cannot get it, write to me, I will tell you why it is. Find the SMA concentration in solution as a function of time. Okay. This is the problem here. If you represent it as this is the surface that needs to be treated, this shaded rectangle that is shown here. This is the z axis, which is the distance from the surface. We said that it is placed at the bottom of the vessel, and the liquid here contains the SMA, and the SMA moves from here to the surface to treat the surface. I have converted this to a concentration axis, Ca. Ca is the concentration of the SMA in this space, in the solution space. Okay, that is what we are looking at. So, let us take the system as the solution, that is the space. We are going to focus on the space here. We are going to leave out the surface from our consideration, because we want to know the concentration profiles, the variation of the concentration profiles here with time. That is what is given here, right? Yeah. Find the SMA concentration in solution as a function of time and space. So, we are going to consider the solution as a system. The species, of course, is the surface modifying agent, SMA. We could use the continuity equation, because this is again motion of SMA, right? So, we can use an appropriate coordinate system. In this case, you can see that the motion is only in one dimension. So, rectangular Cartesian coordinate system is the easiest to use, and also C dAB are constants, rho dAB, C dAB, rho dAB are constants. Therefore, we could directly use equation A2 from table 2.3.2-1. Please make a copy of this table, either hard or soft, that you can access the equations from. So, if you write equation A2, it will be this. We have already seen this earlier, dou C dou T plus this is the convective term, convective motion of the liquid, this is the diffusive term, and this is the reaction term. So, here again we said there is no motion of the liquid after the surface is placed at the bottom. Therefore, certainly there are no Vx, Vy, Vz, which are the components of the convective motion or the bulk motion of the liquid. This cannot be put to 0 because there is variation of concentration with time in the system, right. So, that cannot be put to 0, and that complicates things a lot, as you will see. So, here as I said, Vx equals 0, Vy equals 0, Vz equals 0, no convective or bulk motion. Here dy equals 0, it is not a function of y, it is varying only in one dimension, and dz equals 0 because it is not a function of z, and therefore, I think we should call this as x, right. This is actually x, this is not z, okay, that we will do later. We will consider that the variation to be a function of x, that is what we have done here. I have indicated it as z there, please convert that to that coordinate to x, because to be consistent with this. And of course, there is no reaction in the solution. The reaction if happens at the surface of the at the surface that is being modified, and that we have very nicely removed from the system. Okay. Our system does not contain that, and therefore, there is no reaction that is occurring in the system. So, we have this expression dou C dou T equals di dou squared C I by dou Z squared, and therefore, yeah, let me actually correct this here. The Z is still fine. I think here I have indicated it incorrectly. So, let me correct it here so that there is no confusion. Yep. Let me just move this from here to here, and let me slightly move this from here to here, and this here to here, and we are all set. Okay, good. Okay, let us get back to some of this error kept in. I am sorry about that. To repeat, there is no convective motion, therefore, Vx equals 0, Vy equals 0, Vz equals 0, and there is no variation in the y direction of the concentration. The variation is only in the z direction, therefore, that goes to 0, it is not a function of y, and there is no variation in the x direction, and therefore, that is 0. Please consider this as x. Don't spend time to correct that. This has to be x here. There is no reaction, of course, and we have this. Let us call this equation 2.5-1. This is a partial differential equation. There is a variation with time and a variation with space. This is second order variation, excuse me, second order variation with respect to space, and there is a variation with time. So, you need an initial condition to take care of the time variation, you need two boundary conditions to take care of the second order nature of this to solve this differential equation. This you know from your math course. So, the initial condition is something like this: at t equals 0, that is the initial condition, at z much greater than 0, far away from the surface, Ci, the concentration of the SMA in solution, equals a certain standard C0, which is the bulk concentration in the liquid. 2.5-2. Now to the boundary conditions. At all times greater than 0, right from apart from the initial time point, at z equals 0 at the surface, Ci equals Cs. Although the surface is not a part of the system, the layer of liquid that is immediately above the surface is what z equals 0 is. So, there Ci equals Cs, which is the surface concentration at that liquid layer, 2.5-3, and t greater than 0 at z equals infinity, far off Ci equals the same C0, 2.5-4. So, this is what we have here. Now, be prepared for a good amount of math. The only difference between this equation and the very first equation that we got for steady state for a rectangular coordinate system is this term. This term did not exist earlier, this was 0, and that made the solution a lot simpler compared to this. Just one more derivative here completely complicates the solution part of it. But that is okay. The analytical solution has a lot of insights that it can offer, it has a lot of benefits, and that is the reason why we are looking at the analytical solution here. Also, numerical solution, you need another set of skills to be good at numerical solutions. We will not get into too much of numerical solutions in this course. So, anyway, the situation now is you have dou Ci dou t equals di dou squared Ci by dou z squared. Just mentally prepare yourself for some concentrated time, the time that requires concentration. So, this solution of the differential equation will provide the concentration profiles of the surface modifying agent in the solution. That's how we have set up the problem, and that would be at various times. For example, at a certain time there would be a certain profile, at a different time there would be a different profile, at an even different time there would be a third profile, and so on and so forth. Now, again, to make the solution more gently applicable, we are going to express the equation in terms of dimensionless variables, non-dimensional variables. To do that, let us define a theta as Ci minus Co divided by Cs minus Co. Ci is the variable here, Co is the concentration in the bulk, Cs is the SMA at z equals 0, 2.5-5, and let us define a eta as z divided by square root of 4 dit. Okay. This calls for a lot of insight. To define it this way, it calls for a lot of insight. This has already been done. It's a very standard way of solving this. I am not doing this here. This I have directly picked from a certain textbook. So, don't worry about how I would be able to do this without any practice. No, we are not expecting you to do that. However, this is the way to solve this problem, and by repeated seeing of solutions, and if you have insights, you can do this on your own for other things, and that level of manipulation may not be expected in this course. However, so don't worry about how do you come up with this. This calls for a lot of insight, by the way. Okay. This variable especially calls for a lot of insight. This is to give you a preview. This has been defined to convert the partial differential equation into an ordinary differential equation. As you know, ordinary differential equations are far easier to solve than partial differential equation. So, with a lot of insight as to how the solution will progress, this has come up by the first person who came up with this. We are just following it. Okay. So, now that you are clear about that concern of yours, eta equals z by square root of 4 dit. We have defined it this way, equation 2.5-6. As I mentioned, this variable eta has been constructed to allow the possibility of conversion of the PDE into ODE by combining both the independent terms z as well as the time. Okay, the space variable as well as the time variable has been combined very cleverly into this variable, and this formulation is going to help us convert the PDE into a ODE. So, we have constructed theta to be a function of eta, because Ci is a function of eta, a function of space and time, whereas eta again is explicitly a function of z and t. That is how we are starting out. We can use a chain rule and replace dou theta by dou eta here by d theta by d eta. This is the partial derivative here, this is the total derivative here without any loss. Okay. Here theta is only a function of eta, and therefore, this partial can be replaced with the total, and that is a part of the requirement here to convert. So, that is one of the reasons why we have done this. I am just explaining why it is. Do not start thinking about how I am going to do it, do not worry about it for now, or how you are going to do it, do not worry about it for now. Now, using chain rule from 2.5-5, which is this, theta is Ci minus C naught divided by Cs minus C naught. So, we are going to see dou Ci dou T is dou Ci dou T Cs minus C naught theta by C naught, plus C naught, and if you are going to take the different derivative there, then it will become Cs minus C naught d theta by d eta, and by chain rule d eta is also a function of you have d theta by d eta, and here you want the derivative with respect to time, and therefore, dou eta by dou t. You have this here. Go back, do this yourself and verify that you are indeed getting this. Let us call this equation A, slightly different numbering for the manipulation part. The derivative of eta with respect to t, this one, is nothing but what is eta z by square root of 4 dit. So, that becomes the time derivative is here, this is t power minus half that is there. So, if you take this here minus z, and if you take the derivative with respect to time, then you get the rest can remain as they are. You get minus half times t power minus 3 by 2, so you can bring a t out and keep a t inside the half, and therefore, minus z divided by 2t square root of 4 dit. This is nothing but again eta. So, you get minus eta divided by 2t. So, this has been this is what our definition of eta was, and therefore, it becomes minus eta by 2t. Call this B. Now, if you substitute equation B, which is dou eta by dou t equals minus eta by 2t into this, we get dou C by dou t equals, because there is a minus here, minus Cs minus C naught d theta by d eta, and this dou eta by dou t becomes eta by 2t. C. Similarly, the spatial derivatives become transformed as dou Ci dou z equals Cs minus C naught d theta d eta dz. Okay. This you will have to do and confirm yourself. I have shown you how to do this here. Please stop the video here, go back and convert dou C dou z in terms of theta and eta, and see whether you actually get this. We will call this D. Pause, go back, and then you can come back. So, the first derivative was that, and the second derivative dou squared by dou z squared was Cs minus C naught dou z of d theta d eta times d eta dz is what we get. Let us call this equation E. Since dou eta by dou z is 1 by square root of 4 dit, and this is independent of z, okay, this dou eta by dou z is independent of z, dou eta by dou z is actually independent of z, therefore, this is not going to vary with z, we can take that out as a constant. So, if we take that out as a constant, dou squared Ci dou z squared is nothing but Cs minus C naught square root of 4 dit dou z of dou d theta by d eta alone, this being a constant has come out here. So, that can be written as Cs minus C naught square root of 4 dit d eta of dou theta dou z. The order of differentiation does not matter here, so we have switched it around. F. Now, if we apply the chain rule, d theta d eta is d theta dz, or dou theta dou z. We are looking at this. Dou theta dou z is dou theta dou eta dou z. We already saw that we can replace that by the partial by the total, therefore, d theta d eta dou z. D eta dou z is nothing but 1 by square root of 4 dit. So, that comes in here, the remaining is d theta d eta. We will call this G, and if we substitute G into F, that is we are substituting for this, then we get dou squared Ci dou z squared equals Cs minus C naught 4 dit, there is a square root there and square root here, they will combine, d squared theta by d eta squared. So, this is what we get for the second derivative H. Now, by substituting d in H, so d was this dou Ci dou z, right, an expression for that, in H, which is this, then we get this equation. Again, I would like you to verify this. This is, you need to write it down and check, minus eta Cs minus C naught divided by 2t d theta d eta equals di Cs minus C naught 4 dit d squared theta by d eta squared. You can cancel the common terms here, and now this nicely reduces to minus 2 eta, 4 and 2, there is a 2 remaining, d theta d eta equals d squared theta by d eta squared. So, the partial differential equation has been successfully converted into a total differential equation by using some previous insight by somebody else. We will call this equation 2.5-7. The transformed boundary conditions, these are quite easy to see. At eta equals 0, theta equals 1, and at eta tending to infinity, theta equals 0, 2.5-9. I think we have been at this intense mathematical manipulations for a while now. Let me see what the next thing is. Okay, before I do that, I need to tell you this. The variable eta was constructed simultaneously to satisfy both the initial condition as well as the boundary condition, and kind of collapse that into to simultaneously satisfy both these, and that was also a part of the intuitive writing of eta as the way it was written. Okay. What else? Yeah. I think we need to take a break here. We have been at this for this intense working for some time. It will get tiring, and therefore, let us take a break. When we come back in the next class, I will show you the solution of this. There is still many more steps to go for the solution. Just that one more derivative coming in there instead of a 0 has changed the solution from half a page to about 5 or 6 pages. Right? That is what happens, especially when you have partial differential equation. The solution is a lot more involved, but that is the nature of things. Okay. See you in the next class.